Math 2414, Power Series Video 6, fourth example. And I've already got a typo, so let's go fix that. In the previous video, we introduced the Power Series Convergence Theorem, which basically says that power series can only converge one of three ways: at its center, over the entire number line, meaning that it converges no matter what x equals, or on some interval centered at the center with some finite radius, and we have to check the endpoints for convergence. So the rest of the examples in this video are going to be finding the interval of convergence and the radius of convergence for power series. So let's do that for this one. The sum from n equals 0 to infinity of -3 to the nth power times x to the nth power over the square root of n plus 1. We're going to attack all of these the same way by setting up the ratio test. And if we set up the ratio test, we're going to use the ratio test. I just want to see how many times I can say ratio test. All right, using the ratio test, we're going to set up the limit as n approaches infinity of the absolute value of the ratio of consecutive terms. So the next term over the current term. But just like I mentioned before, when your terms are ratios already, fractions if you will, then it's actually easier to set up the next term times the reciprocal of the current term. So let's set up the next term. The next term is what we would get when we let n become n plus 1. So -3 to the n plus 1 times x to the n plus 1 over the square root of n plus 1 plus 1. The second plus 1 being the part of the original expression. Now, if you want to pay close attention, you can streamline some moves. For example, it's kind of a waste of time to write n plus 1 when I could just write n plus 2. But don't streamline if you're not sure. Make 100% sure you're okay with skipping minor steps. And then we divide that by the current term, which is the same as multiplying it times its reciprocal. So we will reciprocate and put the square root of n plus 1 over -3 to the n, x to the n. Things where the n shows up as powers, there's usually some canceling. These x's cancel all but one of those. And the same thing for the -3's. All of those -3's cancel all of those except one of them. You can tell there's one left over by subtracting the exponents. So we got a -3 and an x inside of an absolute value and independent of the n. So we can go ahead and pull that out of the limit since its value does not depend on the limit. If you notice that a -3 just became a +3 because I literally took its absolute value. So why is it still living inside the absolute value? I don't know. The x, on the other hand, could be positive or negative, so it has to stay in there. And let's take a look at the limit of what remains. Now, what remains on the top and the bottom are both square roots. And anytime you have one square root over another, you can just merge them into a single square root. So we have the limit of the absolute value of the square root of n plus 1 over n plus 2. Technically, the absolute values aren't necessary here because square roots come out positive by definition. And square root being a continuous function on its domain allows us to move the limit inside. So again, being super nitpicky here, we don't really need the square root, and we can move the limit inside because square roots are continuous on their domains, I should say. Well, choose your plan of attack for the limit of that rational function. L'Hopital's rule, multiply both sides by the reciprocal of the highest power in the denominator, or simply say, well, the degrees match, and so the limit's going to be the ratio of leading coefficients. So that limit is 1, which means that our limit for the ratio test is 3 times the absolute value of x times the square root of 1. But the square root of 1 is 1, and 1 times anything is itself. So it's really kind of redundant to write times the square root of 1. All right, we've got our limit to the ratio test, and to get convergence, we need to solve that limit, 3 absolute value of x is less than 1. Well, this is pretty easy to solve. Isolate the absolute value, We get the absolute value of x is less than 1/3. Then that means that x has to be between 1/3 and negative 1/3. Now, that doesn't quite end it because it tells us that our solution is going to include this interval, which is centered at 0. But the ratio test does not know what to do when your limit is equal to 1. In other words, if this said equal, then we don't know if we get convergence or divergence. So you must check the endpoints individually for convergence. Let's start with x equals 1/3. We'll go back to our original series, which is up there. Replace the x with the 1/3. Sum of n equals 0 to infinity of negative 3 to the n, replacing the x with the 1/3 to the n over the square root of n plus 1. Let's see, the 3's I want to cancel, but there's a negative on one and there's a numerator above the other. That's easy enough to fix. Actually, what we can do instead of splitting things to expose 3 to the n's canceling is we can merge them into one product to the nth power since both of them have the same exponent. But negative 3 times 1/3 is negative 1. So this is equal to the sum from n equals 0 to infinity and negative 1 to the n over the square root of n plus 1. We got an alternating series. So let's use the alternating series test. By looking at the individual term without the alternator, it would be 1 over the square root of n plus 1. And ask the 3 questions. Is it positive? Yes. Is it decreasing? That should be pretty obvious because as the n gets larger, the numerator approaches infinity, and so the fraction starts collapsing, and it does approach 0. So this series satisfies all 3 criteria in the alternating series test, and as a conclusion, the series converges. And more specifically, it converges, not converses, converges at x equals 1/3. So now we know what happens at 1/3, but we also have to check the other end of the interval, negative 1/3. So let's check that on the next page. When x equals negative 1/3, our series n equals 0 to infinity becomes n equals 0 to infinity, negative 3 to the n. It was x to the n, but now the x is negative 1/3 over the square root of n plus 1. Just like before, we have a product of 2 things with the same exponent. So we can rewrite it as a single exponent by multiplying the bases inside the parentheses. But negative 3 times negative 1/3 is 1. And 1 to any power is 1, and so the numerator just becomes, well, 1. Notice this is not an alternating series. It did have an alternator, but we threw in another alternator, and they basically merged and said, we're not alternating anymore. We're always positive 1. So we can't use the alternating series test. We could use, well, there's a variety of things we could use. We could use the integral test. We could use comparison test. We could use the limit comparison test. Whenever you're examining types of tests, look for the thing that's easiest for you. I'll choose the integral test when the expression is easily integrable and it meets all the criteria. The criteria for the integral test is that this guy is positive, decreasing, and approaching 0. Wait, was it all 3? Or am I thinking alternating series? Regardless, we're going to play out the integral test on this guy. The integral test says that the series will converge if and only if the integral will converge, in this case, the integral from 0 to infinity of 1 over the square root of x plus 1 dx. If we do it properly, if we do the improper integral properly, we take the limit as t approaches infinity or whatever variable you want to use of the integral from 0 to t, and let's rewrite that as x plus 1 to the negative 1/2. dx. Technically, you could do a substitution, but if you said u equals x plus 1, then du is equal to dx. And I've said before, when you do a substitution but get du equals dx, you don't have to bother doing the substitution. Just take the antiderivative the way you normally would. There's no du package to balance out. So let's integrate this by adding 1 to the exponent. Negative 1/2 plus 1 is 1/2. Then multiplying by the reciprocal. Take the derivative real quick just to make sure. I didn't leave room in front for my limit, so let's fix that. Limit as t approaches infinity of this guy being evaluated from 0 to t. So this will give us the limit as t approaches infinity. Substitute the upper limit to get 2 times t plus 1 to the 1/2, but let's go ahead and write it as the square root of t plus 1. Minus, substitute the lower limit to get 2 times the square root of 0 plus 1. That's equal to 2, the second half of the subtraction problem, but it doesn't matter. This limit approaches infinity. So since the integral diverges, by the integral test, the series diverges. Therefore, the series diverges. So let's see what we ended up with. At negative 1/3, we got divergence. At positive 1/3, we got convergence, which means on our number line, if we were to shade between negative 1/3 and 1/3, then we would want a bracket on the 1/3, since we had convergence there, a parentheses on the negative 1/3, since we had divergence there, and everything in between. And now it's easy to answer our questions. The center is at 0, but let's be honest, we knew that all along. We knew the center was 0 all along, because if we go back to the very original series, what's being subtracted from this x? Nothing, literally. So we knew the center was 0 from the beginning. The only thing we didn't really know was the radius, and hence the interval. This is centered at 0. And maybe I should use A for center, which sounds really silly. Why don't you use C for center? Because C was already used to represent coefficient. Our radius is the distance from the center to either endpoint, but no matter which direction you go, the radius is 1/3. And our interval of convergence is negative 1/3, comma 1/3, parentheses on the negative 1/3 because divergence occurred when x equals negative 1/3. Bracket on the 1/3 because we got convergence when x was equal to 1/3.